Hi everyone, welcome to this video about the first lesson in the conservation of mass and reactivity scheme, usually taught around year 8. This first lesson is called What is Burning, and it's one of our historical case study lessons. And really the idea of this lesson is not, it's partly to study some history because that's interesting and an important part of what we should pass on to students at school, but really it's about introducing a concept. And it's about introducing this concept of conservation of mass, which is fundamental to modern chemistry. And sometimes it's so obvious to us as experts that we kind of overlook its importance when we teach it to students. So I've chosen burning because this is a really nice way to illustrate it. And what this lesson is going to cover is the phlogiston theory, an older theory, and it's precursor to the kind of history of science stuff that students will study at GCSE to do with models of the atom. So I'd probably start by taking a box of matches and lighting a match. You can do this under the visualizer with your students, or however you wish to do. So if I light the match here, I can show them what's going on. And what you want them to observe is what's happening to the match. Now I'm sitting at a wooden desk and I'm hanging this over a book, so this is probably not best practice. But anyway, hopefully what they'll see is the match gets smaller. And they'll be familiar with this. I'm sure they've used matches at other times. I'm just going to move this out of the way. Maybe I should put it up here. So we can see the match. And what you want them to notice is that the match gets smaller and smaller and smaller and smaller until at some point it will kind of burn away. So what you're left with, that's getting very smoky now, but what you're left with is something smaller than what you started with. Now, students will have all sorts of ideas on what's going on during burning. I don't think I really understood fire. Maybe I'm not sure I even understand fire now. It's kind of a confusing thing, even though it's something so kind of basic to human existence. But what we really want to kind of get them thinking about is, well, okay, we can see that this has become smaller. It's kind of become withered. Obviously, it's blackened a bit and stuff as well. So what's going on? And what we want to do is show what scientists thought was happening during burning, because this is a really nice illustration of why it's so important to use this concept of the conservation of mass. Now, that's just a nice introduction with the match, but what we're going to think about, and there'll be a whole lesson on this later in the scheme, but this is just an introduction. We're going to think about what happens when you burn metals. So we're going to use the guest-deduced check model, and that's been introduced in an earlier lesson. This is based on kind of Karl Popper's theory about science, about how scientific knowledge develops. And what we want to think about is, similar to the match that seems to get smaller, well, what do we think is happening when we burn metals? So let's start and imagine we've got a piece of magnesium like this. And I would draw this for students and get them to draw with me. And let's say we've got 10 grams of magnesium. So I looked up before recording this video, magnesium was actually discovered by Joseph Black, one of my scientific heroes from Scotland in the 1700s. And I haven't looked up the history fully, but Joseph Black was one of the first people to recognise the importance of conservation of mass. So it's kind of appropriate that he discovered magnesium, because that's the classic demonstration. So what we're going to do is zoom in to think about what scientists thought it looked like inside a piece of magnesium. And I'm not going to draw loads and loads of particles. Remember, this is year 8, so I'm just keeping it at the particle model right now. I'm not going to do atoms and delocalized electrons, all that stuff. Don't really need to. At this stage, it's fine just to draw some particles like this. So I'm just going to draw 6 particles, because I'm going to keep this really, really simple, just like that. And what we want to tease out with the match example is, it looks like, because the match has got smaller, it looks like the match has lost something. And what they thought the match had lost is something called phlogiston. So we can show that inside here. They didn't think in terms of particles. It's a bit of an anachronism, but again, this is to illustrate the scientific concept. It's not about perfect historical accuracy. What we can show is that what they thought was that inside a metal, same as inside a match, you had some particles of the substance, but you also had some particles of what we're going to call in this case phlogiston. So this is what it would look like inside the match. You'd have some magnesium particles and you'd have some phlogiston particles, let's say. So the next question we have to ask ourselves is, okay, if this idea that all substances contain this phlogiston, which is released by burning, well, let's work out what we'd expect to happen if that was true. That's what we mean by deducing. So what I'm going to do here is draw a little tripod with a gauze on top. I'm going to draw my piece of magnesium like this, and I'm going to imagine I've set it on fire. And you might want to demo this. Again, students will be doing this in a later lesson, but you might want to demo it just to, give them something to see. And obviously, students love burning things and seeing explosions. So what we thought was happening during this stage is as follows. If we zoom in on what's going on here, and I'm going to draw my little box so it's kind of half on the magnesium and half above. I'm going to or something like this. And what we can see here is, sorry, it's just started raining where I am. What we can see here is, now what we would see inside here is the magnesium particles. They've been left behind. And what scientists thought was happening during burning was that those phlogiston particles escaped. So we can draw those up here like this. And effectively what's happening then is that phlogiston is being released to the surrounding air. So we've got phlogiston like this out here. And then this is the crucial bit. We want to think, well, okay, if we started with 10 grams of magnesium and then we burn it, and if we assume this is true, we release phlogiston out into the surroundings, I want to ask my students, well, what would you expect to happen? What would the mass of the magnesium be, or the product be, whatever's left behind, after burning has taken place? And I might do a kind of whole class check, thumbs up, thumbs down. I say, okay, what would you expect to happen? Is the mass going to increase, decrease, stay the same? And what I want them to think about is, if this theory was true, then what we'd expect is that the mass of the product is going to be lower than 10 grams. It's going to decrease. Now what we can do then is check and say, well, okay, if you actually do this, and again, this is where a demo is quite good, but you might just want to do a kind of thought experiment at this stage and then do the experiment properly in a later lesson. But what we end up with is this kind of white powder here, kind of grey white powder. We don't need to tell them what that's called now, because we'll come to that part of the story later. But if you measure the mass, we can make up some numbers here. Actually, this isn't less than 10 grams, it's more than, let's say, it's 12 grams. And again, this is where we want to really get them thinking scientifically. Well, what does that mean? We thought if phlogiston was true, the mass should go down, but when we actually do the experiment, the mass always seems to go up. What does that mean? Well, that means that the guess is wrong. And I might do that in a different colour just to really illustrate. In fact, let's be really assertive here. Let's use red. What that means is the guess is wrong. And this is what you want to remind them of. This is really the characteristic feature of scientific knowledge, is if an experiment shows that the guess is wrong, well, we need a new guess. So then we can tell them, you can tell them about Joseph Black if you like, but I'm just going to simplify the story here and tell them about a chap called Lavoisier. So Lavoisier had a different view about what was going on. He realised that actually this guess cannot be true. And the reason it can't be true is because he thought, well, hang on, mass needs to be conserved. And it's worth emphasising here, I just drew this and I didn't really pay much attention, but I did this quite deliberately here. I made sure that I was going to draw 6 particles here, and in this diagram I also drew 6 particles. And what Lavoisier realised was that what we must always assume about a chemical reaction is that no particles can ever be created or destroyed. we have to assume that mass is conserved. We have to assume that the total number of particles you start with is the total number of particles you end with. And this is why he realized that this result, the fact that the mass went up instead of down, had to disprove the phlogiston theory. And what's interesting is the chemists of the 16 and 1700s, obviously chemistry had derived from alchemy. People thought it was kind of magic. They were trying to make gold out of the base metals and so on. They didn't really think conservation of mass was a big deal. And that was the genius of Lavoisier. He realized that nothing could work in chemistry unless you assumed the total mass of the products was the same as the total mass of the reactant. And what we want to get across to students here is not just remember this law. What we want them to understand is that this law is a rule that we impose on the chemical reactions we observe, because that's the only way they can make sense. Chemical reactions only make sense if we assume that the total number of particles stays the same. They just rearrange themselves. They're not created or destroyed. Anyway, that's a bit of a long-winded way of talking, but these are quite subtle points to try and get across. But what Lavoisier thought was that, okay, if the mass is going up, well then, phlogiston can't be being lost. That just makes no sense. Clearly, something must be taken in from the air instead. He flipped the way of thinking about it, and that helped to explain this result. So let's say we start with our 10 grams of magnesium. The way Lavoisier thought about it was to say, okay, what would I see inside here? Again, I'm just going to draw, to keep this really simple, I'm going to draw just 6 particles. Make sure I'm consistent with my drawings here. So that's Mg, 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 Mg. And he thought, actually, whereas beforehand metals had been understood to be compounds, he said, no, I think actually this magnesium metal must be an element. It's only got one type of particle. And again, this is why Lavoisier was such a genius, because he flipped the way we thought about chemistry on its head. So what Lavoisier said was, okay, if that was true, and I burn this magnesium, as we saw before, and I get this kind of big flash of light, he thought that instead of phlogiston being given out to the surroundings, he assumed that oxygen must be taken in. So I'm going to draw some arrows going in like this. He realized that what was happening was something was being taken in from the air, and it was actually Lavoisier himself who named it oxygen. There is another story about that. He kind of named it incorrectly. It means acid former. Oxygen means acid former. Now we know that hydrogen is the acid former, but maybe I wouldn't go into that with year 8. Anyway, what he thought was happening then, if we zoom in to give a particle diagram like this, what he thought was happening was as follows. So if these are our 6 magnesium atoms, and again I'm going to be really careful to draw the same number here, because with all these diagrams, having the same number of particles before and after is what really illustrates the idea of conservation of mass. I'm then going to say, well, what he thought was happening was there must be some oxygen particles out here in the air, like that, and I've now drawn 7. Whoops. So I just want to do 6 here. So these are oxygen particles out in the air. And what he thought was happening here was that these oxygen particles must be joining with the magnesium. So we can show this like this. The wrong way, but anyway. That somehow the oxygen and the magnesium are combining. Now, if that guess was true, then what you'd expect to happen is that the mass of the product should increase. It should be greater than what we started with, because we've added particles into this substance. So the mass should increase. And again, I might check for understanding if I was teaching the students with thumbs up, thumbs down, so I can get a whole class response. So when we check that, well, as we saw earlier, this is exactly what happens. Something like this. And if we were to zoom in on this, I might show students, well, what would you expect this to look like? And this is where I'm illustrating what's going on in a chemical reaction. If we were to zoom in on this white powder that we talked about before, well, now I'm going to try and make my particle diagrams a bit neater. Now I'm going to draw 12 particles, and obviously magnesium and oxygen is a nice example because it does kind of look like this. We're not going into ionic bonds or anything like that at this stage, but in simple terms, it kind of looks like this. We've got MgO, MgO. I realised we get OMG, which I'm sure students will find entertaining. OMG, and then MgO, MgO. So what we've got here, and again, this is some nice kind of revision of things that they probably would have done in year 7. And what we've got here is a compound, because it's got 2 types of atoms, and it was Lavoisier who first realised that the product of combustion or burning is a compound. It's not it's not an element that's been had its phlogiston liberated. And this compound, because it's got magnesium and oxygen, we would call this magnesium oxide. Measure the mass, and we get 12 grams. Well, look, the mass has increased. It's gone from 10 to 12. That says that Lavoisier's guess about what's going on here is correct. So we can put some sort of tick there to show that that guess is correct. And actually, the system that Lavoisier built, the chemical system, the way he kind of mapped everything out, is still pretty much the one we use today. Obviously, we've refined it. Now we know lots about electrons and the structure of the nucleus and all of this other sort of stuff. But in terms of the system of elements and in very simple terms, how they interact with one another, Lavoisier was the architect. And again, what this serves to show to students is the reason we had to throw out this phlogiston theory, which, remember, go back to the match, it seems kind of intuitive that something's being lost here because that's got smaller. It was on fire and then it seemed to lose something to the air. That's the intuitive picture that students may well still hold, but we have to throw that out if we believe in the conservation of mass. And this is why that's such a powerful concept, is because it allows us to think in ways that we wouldn't be able to think otherwise. So that is the introductory lesson on conservation of mass and bringing in this concept. And what we do in the next few lessons in this scheme, which have not been planned by me, they've been planned by my colleague Rowena Jones at Parkhouse School in Newbury. What we do in those lessons is really explore conservation of mass through lots of practical experiments. So it's them doing things like burning magnesium and looking at it and using this concept to understand what's going on. I hope that's been useful, and yeah, I look forward to doing some more chemistry videos soon.